good day everyone. My name is Miriam Nicole Barrios, and for today's video, we will tackle about entropy changes and irreversible processes. So, next. First, let's define what is entropy. According to the book Principle of Physics, entropy is another state of variable related to the second law of thermodynamics. So, for the reversible processes, the entropy as a state of universe remains constant. But for irreversible processes, the entropy of the universe will increase. So, how can we calculate entropy changes for irreversible processes? So, we can calculate entropy changes for irreversible processes by dividing irreversible processes between the same two equilibrium states and computing QR over T for the reversible processes. So, before we continue, let's break down uh, the components. So QR represents the differential amount of heat transferred reversibly, and thermodynamics QR typically denotes heat transfer occurring in an idealized reversible processes. While T is a absolute temperature at which the reversible heat transfer occurs. So this equation describes the ratio of an infinitesimal amount of heat transfer reversibly to the temperature. This ratio is indicative of the infinitesimal change in associated with an infinitesimal heat transfer at the specific temperature. So, in irreversible processes, it is critically important to distinguish between the Q, the the actual energy transfer in the process, and the QR. The energy would have been transferred by heat along the reversible path between the same states. So, for example, if an ideal gas expands diabatically into a vacuum, Q is equals to zero. But change in, en- entropy cannot equal to zero because Q R cannot equal to zero. The reversible path between the same two states is reversible. Isothermal expansion that gives change of entropy is greater than zero. So, when dealing the interacting objects that are not isolated from the environment, we must consider the change of entropy for the system in its environment. When the two objects interact in an irreversible process, the increase in entropy of one part of the universe is greater than the decrease in entropy of the other part. Hence, we conclude that the change in entropy of the universe must be greater than zero for an irreversible process and equal to zero for the reversible adiabatic process. Ultimately, the entropy of the universe should reach a maximum value. At this point, the universe will be in a state of uniform temperature and density. So, all physical, chemical, and biological processes will cease because a state of perfect disorder implies that no energy is available for doing work. This gloomy state of affairs is sometimes referred to as the heat death of the universe. So before we end this discussion, let me ask you a question. It is true or false that the entropy change in the adiabatic process must be equal to zero because Q is equals to zero. So that's all for today. Again, this is Miriam Nicole Barrios. Thank you for listening.